In Part A of the chapter, we treated insurance markets without actually referring to the risk that insurance policies are meant to insure against. We did this so that we can treat the adverse selection problem without actually having covered the topic of risk in Chapter 17. We now assume that you've covered the topic of risk in Chapter 17 and illustrate the adverse selection problem in insurance markets where we explicitly model the risk that is insured against. We'll assume that all individuals face the possibility of a good outcome and a bad outcome, where consumption in the good outcome is x2 and consumption in the bad outcome is x1. In our example here, x2 will be 250 and x1 will be 10. But not everyone faces the same probability of the good versus the bad outcome. We'll have a low-risk type, delta, that faces a probability delta of the bad outcome occurring, and another high-risk type, theta, who faces a probability of theta that the bad outcome will occur. Since the theta type is the high-risk type, we're assuming that theta is greater than delta. An insurance contract is then a combination of an insurance premium and an insurance benefit. The insurance premium P has to be paid regardless of whether the good or the bad state occurs. The benefit level B is paid if the bad state occurs. Thus, a consumer who purchases an insurance policy PB will have consumption level X1 plus B minus P if the bad state occurs, and consumption level X2 minus P if the good state occurs. We can then illustrate indifference curves, where on the horizontal axis we put the benefit level B, and on the vertical axis we put the premium P. Individuals become better off as the benefit level B increases and the premium P decreases. In other words, within our graph, consumers become better off as they move to the southeast in the graph. For a low-risk delta type, these indifference curves emerge mathematically from the expected utility function defined in equation 22.2. In Chapter 17, we defined actuarially fair insurance policies as those that lead to zero profit for insurance companies. For a low-risk delta type, an insurance company would expect to pay out the benefit level B with probability delta. It would collect the premium P with probability 1, because the consumer has to pay it regardless of whether the good or the bad state hits. Thus, in order for the insurance company to make zero profit, P has to be equal to delta B. This allows us to illustrate the set of actuarially fair insurance policies for low-risk delta types as a line defined by the equation P is equal to delta B. When offered a full menu of actuarially fair insurance policies, a consumer in our graph will then optimize at the insurance policy that has a benefit level of 240 and a premium of 60. We know from Chapter 17 that risk-averse individuals will fully insure when offered a full set of actuarially fair insurance contracts. And in our graph, the optimal insurance policy of a benefit level of 240 and a premium of 60 is in fact the policy that fully insures this individual who faces a bad outcome of x1 equal to 10, a good outcome of x2 equal to 250, and a probability delta of 0.25.